Hello everyone, it's Carter from 19. Today is day 21 in my challenge day. And what I'm going to do is just keeping the your network course week of 2. Okay, let's start.
In the last video, we talked about exponentially weighted averages. This will turn out to be a key component of several optimization algorithms that you use to train your neural networks. So in this video, I want to delve a little bit deeper into intuitions for what this algorithm is really doing. Recall that this is the key equation for implementing exponentially weighted averages. And so if beta equals 0.9, you got the red line. If it was much closer to 1, if it was 0.98, you get the green line. And if it's much smaller, maybe 0.5, you get the yellow line. Let's look at a bit more at the math to understand how this is computing averages of the daily temperature. So here's that equation again, and let's set beta equals 0.9 and write out a few equations that this corresponds to. So whereas when implementing it, you'd have t going from 0 to 1 to 2 to 3 increasing values of t. To analyze it, I've written it with decreasing values of t, right? And this goes on. So let's take this first equation here and understand what V100 really is. So V100 is going to be let me reverse these two terms. This is going to be 0.1 times theta 100 plus 0.9 times whatever the value was on the previous day. Now, but what is V99? Well, we can just plug it in from this equation. So this is just going to be 0.1 times theta 99. And again, I've reversed these two terms, right? Plus 0.9 times V98. But then what is V98? Well, you can just get that from here. So you can just plug in here 0.1 times theta 98 plus 0.9 times V97, and so on. And if you multiply all of these terms out, you can show that V100 is 0.1 times theta 100 plus, now let's look at coefficient on theta 99. It's going to be 0.1 times 0.9 times theta 99. Now let's look at the coefficient on theta 98. There's a 0.1 here times 0.9 times 0.9. So if you expand out the algebra, this becomes 0.1 times 0.9 squared times theta 98. And if you keep expanding this out, you find that this becomes 0.1 times 0.9 cubed theta 97 plus 0.1 times 0.9. to the fourth times theta 96 plus dot dot dot. So this is really a weighted sum and thus a weighted average of theta 100, which is the current day's temperature. If we're looking from a perspective of V100, which you calculate on the 100th day of the year. But so is a sum of theta 100, theta 99, theta 98, theta 97, theta 96, and so on. So one way to draw this in pictures would be if let's say we have some number of days of temperature. So this is theta and this is T, right? So theta 100 would be some value, then theta 99 would be some value, theta 98. So these are, so this is T equals 100, 99, 98, and so on, right? So you have some number of days of temperature. And what we have is then an exponentially decaying function. So starting from 0.1 to 0.9 times 0.1 to 0.9 squared times 0.1 to, and so on. So you have this exponentially decaying function. And the way you compute V100 is you take the element-wise product between these two functions and sum it up. So you take this value, theta 100 times 0.1, times this value, theta 99, times 0.1 times 0.9, that's the second term, and so on. So it's really taking the daily temperature, multiplying with this exponentially decaying function, and then summing it up. And this becomes your V100. It turns out that up to details I'll talk about later, but all of these coefficients add up to 1, or add up to very close to 1, up to a detail called bias correction, which we'll talk about in the next video. But because of that, this really is an exponentially weighted average. And finally, you might wonder, how many days temperature is this averaging over? Well, it turns out that 0.9 right, to the power of 10 is about 0.35. And this turns out to be about 1 over e, 1 over the base of natural logarithms. And more generally, if you have 1 minus epsilon, so in this example, epsilon would be 0.1. So if this was 0.9, then 1 minus epsilon to the 1 over epsilon, this is about 1 over e. This is about 0.34, 0.35. And so, in other words, it takes about 10 days for the height of this to decay to, around 1/3, or really 1 over e of the peak. So it's because of this that when beta equals 0.9, we say that this is as if you're computing an exponentially weighted average that focuses on just the last 10 days temperature, because it's after 10 days that the weight decays to, less than about a third of the weight of the current day. Whereas in contrast, if beta was equal to 0.98, then, well, what do you need 0.98 to the power of in order for this to be really small? It turns out that 0.98 to the power of 50 will be approximately equal to 1 over e. So the weight will be pretty big. It'll be bigger than 1 over e for the first 50 days, and then it'll decay quite rapidly over that. So intuitively, this is a hard and fast thing. You can think of this as averaging over about 50 days temperature, because in this example, to use the notation here on the left, is as if epsilon is equal to 0.02, so 1 over epsilon is 50. And this, by the way, is how we got the formula that we're averaging over 1 over 1 minus beta, or so days. Right here, epsilon really plays the role of 1 minus beta. It tells you up to some constant roughly how many days temperature you should think of this as averaging over. But this is just a rule of thumb for how to think about it, and isn't a formal mathematical statement. Finally, let's talk about how you actually implement this. Recall that we start off with V0 initialized as 0, then you compute V1 on the first day, V2, and so on. Now, to explain the algorithm, it was useful to write down V0, V1, V2, and so on as distinct variables. But if you're implementing this in practice, this is what you do. You initialize V to be equal to 0, and then on day 1, you would set V equals beta times V plus 1 minus beta times theta 1. And then on the next day, you would update V to be equal to beta V plus 1 minus beta theta 2, and so on. And I'm sometimes going to use this notation, V subscript theta, to denote that V is computing this exponentially weighted average of the parameter theta. So just to say this again, but in a for loop format, you set V theta equals 0, and then repeatedly, kind of on each day, you would get next theta t, and then set V theta gets updated as beta times the old value of V theta plus 1 minus beta, times the current value of V theta. So one of the advantages of this exponentially weighted average formula is that it takes very little memory. You just need to keep, this one row number in computer memory, and you keep on overwriting it with this formula based on the latest value that you got. And it's really this reason, the efficiency, it just takes, one line of code basically, and just storage and memory for a single row number to compute this exponentially weighted average is really not the best way, not the most accurate way to compute an average. If you were to compute a moving window where you explicitly sum over the last 10 days, the last 50 days temperature, and just divide by 10 or divide by 50, that usually gives you a better estimate. But the disadvantage of that, of explicitly keeping all the temperatures around and summing the last 10 days, is it requires more memory, and it's just more complicated to implement, and it's computationally more expensive. So for things, and we'll see some examples in the next few videos, where you need to compute averages of a lot of variables, this is a very efficient way to do so, both from a computation and memory efficiency point of view, which is why it's used a lot in machine learning. Not to mention that it's just one line of code, which is maybe another advantage. So now you know how to implement exponentially weighted averages. There's one more technical detail that's worth you knowing about called bias correction. Let's see that in the next video. And then after that, you'll be able to use this to build a better optimization algorithm than the straightforward gradient descent. You've learned how to implement exponentially weighted averages. There's one technical detail called bias correction that can make your computation of these averages more accurately. Let's see how that works. In the previous video, you saw this figure for beta equals 0.9, this figure for beta equals 0.98, but it turns out that if you implement the formula as written here, you won't actually get the green curve when, say, beta equals 0.98. You actually get the purple curve here. And you notice that the purple curve starts off really low. So let's see how to fix that. When you're implementing a moving average, you initialize it with v0 equals 0, and then v1 is equal to 0.98 v0 plus 0.02 theta 1. But v0 is equal to 0, so that term just goes away. So v1 is just 0.02 times theta 1. So that's why if the first day's temperature is, say, 40 degrees Fahrenheit, then V1 will be 0.02 times 40, which is 0.8. So you get a much lower value down here. So it's not a very good estimate of the first day's temperature. V2 will be 0.98 times V1 plus 0.02 times theta 2. And if you plug in V1, which is this, down here, and multiply it out, then you find that V2 is actually equal to 0.98 times 0.02 times theta 1 plus 0.02 times theta 2, and that's 0.0196 theta 1 plus 0.02 theta 2. So again, assuming theta 1 and theta 2 are positive numbers, when you compute this, V2 will be much less than theta 1 or theta 2. So V2 isn't a very good estimate of the first 2 days' temperature of the year. So it turns out that there's a way to modify this estimate that makes it much better, that makes it more accurate, especially during this initial phase of your estimates, which is that instead of taking VT, take VT divided by 1 minus beta to the power of t, where t is the current day that you're on. So let's take a concrete example. When t is equal to 2, 1 minus beta to the power of t is 1 minus 0.98 squared, and it turns out that this is 0.0396. And so your estimate of the temperature on day 2 becomes V2 divided by 0.0. 0.0396. And this is going to be 0.0196 times theta 1 plus 0.02 theta 2. You notice that these two things adds up to the denominator 0.0396. And so this becomes a weighted average of theta 1 and theta 2, and this removes this bias. So you notice that as t becomes large, beta to the t will approach 0, which is why when t is large enough, the bias correction makes almost no difference. This is why when t is large, the purple line and the green line pretty much overlap. But during this initial phase of learning, when you're still warming up your estimates, when bias correction can help you to obtain a better estimate of the temperature. And it's this bias correction that helps you go from the purple line to the green line. So in machine learning, for most implementations of the exponentially weighted average, people don't often bother to implement bias correction because most people would rather just wait that initial period and have a slightly more biased estimate and then go from there. But if you are concerned about the bias during this initial phase while your exponentially weighted moving average is still warming up, then bias correction can help you get a better estimate early on. So with that, you now know how to implement exponentially weighted moving averages. Let's go on and use this to build some better optimization algorithms. There's an algorithm called momentum, or gradient descent with momentum, that almost always works faster than the standard gradient descent algorithm. In one sentence, the basic idea is to compute an exponentially weighted average of your gradients, and then to use that gradient to update your weights instead. In this video, let's unpack that one sentence description and see how you can actually. In this video, let's unpack that one basic idea is to compute an exponentially weighted average of your gradients, and then to use that gradient to update your weights instead. In this video, to use that gradient to update, compute an exponentially weighted average of your gradients, and then to use that gradient to update your weights instead. In this video, let's unpack that one sentence description and see how you can actually implement this. As the most of an example, let's say that you're trying to optimize a cost function which has contours like this. So the red dot denotes the position of the minimum. Maybe you start a gradient descent here, and if you take one iteration of gradient descent, either batch or mini batch gradient descent, maybe you end up heading there. But now you're on the other side of this ellipse. You kind of, and if you take another step of gradient descent, maybe you end up doing that. And then another step, and so on. And you see that gradient descents will, sort of take a lot of steps, right? And just slowly oscillate um, toward the minimum. And these up and down oscillations slows down gradient descent and prevents you from using a much larger learning rate. In particular, if you were to use a much larger learning rate, you might end up overshooting and end up diverging like so. And so the need to prevent the oscillations from getting too big forces you to use a learning rate that's not itself too large. Another way of viewing this problem is that on the vertical axis, you want your learning to be a bit slower because you don't want those oscillations. But on the horizontal axis, you want faster learning, right? Because you want it to aggressively move from left to right toward that minimum, toward that red dot. So here's what you can do if you implement gradient descent with momentum. On each iteration, or more specifically, during the gradient descent algorithm. But now you're on the other side, and these up and down oscillations slows down gradient descent and prevents you from using a much larger learning rate. In particular, if you were to use a much larger learning rate, you might end up overshooting and end up diverging like so. And so the need to prevent the oscillations from getting too big forces you to use a learning rate that's not itself too large. Another way of viewing this problem is that on the vertical axis, you want your learning to be a bit slower because you don't want those oscillations. But on the horizontal axis, you want faster learning, right? Because you want it to aggressively move from left to right toward that minimum, toward that red dot. So here's what you can do if you implement gradient descent with momentum. On each iteration, or more specifically, during iteration t, you would compute the usual derivatives dw, db. I'll omit the superscript square bracket else, but you compute dw, db on the current mini batch. And if you're using batch gradient descent, then the current mini batch would be just your whole batch. And this works as well for batch gradient descent. So if your current mini batch is your entire training set, this works fine as well. And then what you do is you compute v dw to be beta vdw plus 1 minus beta dw. So this is similar to when we're previously computing v theta equals beta v theta u, compute dw db on the current mini batch. And if you're using batch gradient descent, then the current mini batch would be just your whole batch. And this works as well for batch gradient descent. So if your current mini batch is your entire training set, this works fine as well. And then what you do is you compute v dw to be beta vdw plus 1 minus beta dw. So this is similar to when we're previously computing v theta equals beta v theta plus 1 minus beta theta t, right? So it's computing moving average of the derivatives for w you're getting. And then you similarly compute vdb equals that plus 1 minus beta times dB. And then you would update your weights using W gets updated as W minus the learning rate times, instead of updating it with dW, with the derivative, you would update it with V dW. And similarly, B gets updated as B minus alpha times V dB. So what this does is smooth out the steps of gradient descent. For example, let's say that the last few derivatives you computed were this, 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 this. If you average out these gradients, you find that the oscillations in the vertical direction will tend to average out to something closer to zero. So in the vertical direction, where you want to slow things down, this will average out positive and negative numbers. So the average should be closer to zero. Whereas on the horizontal direction, all the derivatives are pointing to the right in the horizontal direction, so the average in the horizontal direction will still be pretty big. So that's why with this algorithm, with a few iterations, you find that the gradient descent with momentum ends up eventually just taking steps that are much smaller oscillations in the vertical direction, but are more directed toward the horizontal, to just moving quickly in the horizontal direction. And so this allows your algorithm to take a more straightforward path, or less, to damp out the oscillations in its path to the minimum. One intuition for this momentum, which works for some people and not for everyone, is that if you're trying to minimize a bow-shaped function, right? This is really the contours of a bow. I guess I'm not very good at drawing. But you're trying to minimize this type of bow-shaped function, then these derivative terms you can think of as providing acceleration to a ball that you're rolling downhill. And these momentum terms you can think of as representing the velocity. And so imagine that you have a bow and you take a ball, and the derivative imparts acceleration to this little ball. It's a little ball that's rolling down this hill, right? And so it rolls faster and faster because of acceleration. And beta, because this number a little bit less than 1, displays the role of friction, and it prevents your ball from speeding up without limit. But so rather than gradient descent just taking every single step independently of all previous steps, now your little ball can roll downhill and gain momentum, but it can accelerate down this bow and therefore gain momentum. I find that this ball rolling down a bow analogy, it seems to work for some people who enjoy physics intuitions, but it doesn't work for everyone. So if this analogy imparts acceleration to, you can think of as representing the, is that if you're trying to minimize a bow-shaped function, right? This is really the contours of a bow. I guess I'm not very good at drawing. But you're trying to minimize this type of bow-shaped function, then these derivative terms you can think of as providing acceleration to a ball that you're rolling downhill. And these momentum terms you can think of as representing the velocity. And so imagine that you have a bow and you take a ball, and the derivative imparts acceleration to this little ball. It's a little ball that's rolling down this hill, right? And so it rolls faster and faster because of acceleration. And beta, because this number a little bit less than 1, displays the role of friction, and it prevents your ball from speeding up without limit. But so rather than gradient descent just taking every single step independently of all previous steps, now your little ball can roll downhill and gain momentum, but it can accelerate down this bow and therefore gain momentum. I find that this ball rolling down a bow analogy, it seems to work for some people who enjoy physics intuitions, but it doesn't work for everyone. So if this analogy of a ball rolling down a bow doesn't work for you, don't worry about it. Finally, let's look at some details on how you implement this. Here's the algorithm, and so you now have two hyperparameters, the learning rate alpha as well as this parameter beta, which controls your exponentially weighted average. The most common value for beta is 0.9. We're averaging over the last 10 days. Temperature. So this is like averaging over the last 10 iterations gradient. And in practice, beta equals 0.9 works very well. Feel free to try different values and do some hyperparameter search, but 0.9 appears to be a pretty robust value. Well, and how about bias correction, right? So do you want to take VDW and VDB and divide it by 1 minus beta to the t? In practice, people don't usually do this because after just 10 iterations, your moving average will have warmed up and there's no longer a bias estimate. So in practice, I don't really see people bothering with bias correction when implementing gradient descent with momentum. And of course, this process is initialized with VDW equals 0. Note that this is a matrix of zeros with the same dimension as DW, which is the same dimension as W, and VDB is also initialized to a vector of 0, so the same dimension as DB, which in turn has the same dimension as B. Finally, I just mentioned that if you read the literature on gradient descent with momentum, often you see it with this term omitted, with this 1 minus beta term omitted. So you end up with VDW equals beta VDW plus DW. And the net effect of using this version in purple is that VDW ends up being scaled by a factor of 1 minus beta, or really 1 over 1 minus beta. And so when you're performing these gradient descent updates, alpha just needs to change by a corresponding value of or 1 over 1 minus beta. In practice, both of these will work just fine. It just affects what's the best value of the learning rate alpha. But I find that this particular formulation is a little less intuitive because one impact of this is that if you end up tuning the hyperparameter beta, then this affects the scaling of VDW and VDB as well. And so you end up needing to retune the learning rate alpha as well, maybe. So I personally prefer the formulation that I have written here on the left rather than leaving out the 1 minus beta term. But so I tend to use the formula on the left, the printed formula with the 1 minus beta term. But both versions having beta equals 0.9 is a common choice of hyperparameter. It's just that alpha, the learning rate, will need to be tuned differently for these two different versions. So that's it for gradient descent with momentum. This will almost always work better than the straightforward gradient descent algorithm without momentum. But there's still other things we could do to speed up your learning algorithm. Let's continue talking about these in the next couple videos. You've seen how using momentum can speed up gradient descent. There's another algorithm called RMSprop, which stands for root mean square prop, that can also speed up gradient descent. Let's see how it works. Recall our example from before that if you implement gradient descent, you can end up with huge oscillations in the vertical direction, even whilst trying to make progress in the horizontal direction. In order to provide intuition for this example, let's say that the vertical axis is the parameter b and the horizontal axis is the parameter w. Right? It really could be w1 and w2 or some of the standard parameters, but this is named as b and w for the sake of intuition. And so you want to slow down the learning in the b direction or in the vertical direction and speed up learning, or at least not slow it down in the horizontal direction. So this is what the RMSprop algorithm does to accomplish this. On iteration t, it will compute, as usual, the derivatives dw db on the current mini batch. So I was going to keep this exponentially weighted average. Instead of VDW, I'm going to use new notation SDW. So SDW is equal to beta times their previous value plus 1 minus beta times dw squared. I sometimes write this dw star star 2 to denote the exponentiation. Let's just write this as dw squared. So for clarity, this squaring operation is an element-wise squaring operation. So what this is doing is really keeping an exponentially weighted average of the squares of the derivatives. And similarly, we also have SdB equals beta SdB plus 1 minus beta dB squared. And again, the squaring is an element-wise operation. Next, RMSprop then updates the parameters as follows. W gets updated as W minus the learning rate. And whereas previously we had alpha times dW, now is dW divided by square root of S dW. And B gets updated as B minus the learning rate times, instead of just the gradient, this is also divided by, now divided by S dB. So let's gain some intuition about how this works. Recall that in the horizontal direction, or in this example, in the W direction, we want learning to go pretty fast, whereas in the vertical direction, or in this example, in the B direction, we want to slow down or to damp out the oscillations in the vertical direction. So with these terms, SDW and SDB, what we're hoping is that SDW will be relatively small, so that here we're dividing by a relatively small number, whereas SDB would be relatively large, so that here we're dividing by a relatively large number in order to slow down the updates in the vertical direction. And indeed, if you look at the derivatives, these derivatives are much larger in the vertical direction than in the horizontal direction. So, the slope is very large in the b direction, right? So with derivatives like this is a very large dB and a relatively small dW. Because the function is sloped much more steeply in the vertical direction, that is in the b direction, than in the w direction, than in the horizontal direction. And so dB squared would be relatively large, so SdB would be relatively large, whereas compared to that, dW would be smaller, or dW squared would be smaller, and so SdW would be smaller. So the net effect of this is that your updates in the vertical direction is larger in the vertical direction than in the horizontal direction. So, the slope is very large in the b direction, right? So with derivatives like this is a very large dB and a relatively small dW. Because the function is sloped much more steeply in the vertical direction, that is in the b direction, than in the w direction, than in the horizontal direction. And so dB squared would be relatively large, so SdB would be relatively large, whereas compared to that, dW would be smaller, or dW squared would be smaller, and so SdW would be smaller. So the net effect of this is that your updates in the vertical direction are divided by a much larger number, and so that helps damp out the oscillations, whereas the updates in the horizontal direction are divided by a smaller number. So the net impact of using RMSprop is that your updates will end up looking more like this, right? That your updates in the vertical direction get damped out, but then horizontal direction, it can keep going. And one effect of this is also that you could therefore end up looking more like this, divided by a smaller number. So the net impact of using RMSprop is that your updates will end up looking more like this, right? That your updates in the vertical direction get damped out, but then horizontal direction, it can keep going. And one effect of this is also that you could therefore use a larger learning rate alpha and get faster learning without it diverging in the vertical direction. Whereas compared to that, dW will be smaller, or dW squared will be smaller, and so SdW will be smaller. Direction, that is in the b direction, than in the w direction, than in the horizontal direction. And so dB squared will be relatively large, so SDB will be relatively large, whereas compared to that, DW will be smaller, or DW squared will be smaller, and so SDW will be smaller. So the net effect of this is that your updates in the vertical direction are divided by a much larger number, and so that helps damp out the oscillation. Whereas the updates in the horizontal direction are divided by a smaller number. So the net impact of using RMSprop is that your updates will end up looking more like this, right? That your updates in the vertical direction get damped out, but in horizontal direction it can keep going. And one effect of this is also that you could therefore use a larger learning rate alpha and get faster learning without it diverging in the vertical direction. Now, just for the sake of clarity, I've been calling the vertical and horizontal directions B and W just to illustrate this. In practice, you're in a very high dimensional space of parameters, so maybe the vertical dimensions where you're trying to dampen oscillations is some set of parameters W1, W2, W17, and the horizontal dimensions might be W3, W4, and so on, right? And so the separation is a W and B is just for illustration. In practice, dW is a very high dimensional parameter vector. dB is also a very high dimensional parameter vector. But the intuition is that in dimensions where you're getting these oscillations, you end up computing a larger sum or weighted average for these squares of derivatives, and so you end up damping out the directions in which there are these oscillations. So that's RMSprop, and it stands for root mean squared because root mean squared prop, because here you're squaring the derivatives and then you take the square root here at the end. So finally, just a couple last details on this algorithm before we move on. In the next video, we're actually going to combine RMSprop together with momentum. So rather than using the hyperparameter beta, which we had used for momentum, I'm going to call this hyperparameter beta 2, just to not clash, the same hyperparameter for both momentum and for RMSprop. And also to make sure that your algorithm doesn't divide by 0. What if square root of SDW, right, is very close to 0? Then this thing could blow up. Just to ensure numerical stability, when you implement this in practice, you add a very, very small epsilon to the denominator. Doesn't really matter what epsilon is. You use 10 to the negative 8 would be a reasonable default, but this just ensures slightly greater numerical stability that, for numerical round off or whatever reason, that you don't end up dividing by a very small number. So that's RMSprop, and similar to momentum, has the effect of damping out the oscillations in gradient descent, in mean batch gradient descent, and allowing you to maybe use a larger learning rate alpha, and certainly speeding up the learning speed of your algorithm. So now you know how to implement RMSprop, and this will be another way for you to speed up your learning algorithm. One fun fact about RMSprop, it was actually first proposed not in an academic research paper, but in a Coursera course that Jeff Hinton had taught on Coursera many years ago. I guess Coursera wasn't intended to be a platform for dissemination of novel academic research, but it worked out pretty well in that case. It was really from the Coursera course that RMSprop started to become widely known and it really took off. We've talked about momentum, we've talked about RMSprop. It turns out that if you put them together, you can get an even better optimization algorithm. Let's talk about that in the next video.
Okay, I just finished the amount of learning that I should do today. And before I start going to end up this recording, let's recap first. So what I learned today is just about um, some exponentially weighted averages that I learned the previous day. So as I've already seen before in the previous recording, the average, weighted average makes interpolation among the data sets we have in the previous ways. So we can just use a weighted sum by impacting on the current data. It means that we can use data in the dependent way around the true data, and utilizing the data surrounding the true data. In this case, we can handle the gradient descent is also the dependent way, not the independent way, which is leads to some slower learning in the practice. So before we move on to the another optimization algorithm in gradient descent, we need to there's a concept with bias correction because we initialize the v0, which is the initial value in the vt, as a 0, and it makes the values in initial passes is kind of not good. It's made compared to the later on. So by dividing 1 minus beta t, we can remove bias by multiplying a number bigger than 1. But when it goes to the larger t, it converges the vt beta t converges to 0. And we can ignore that the bias correction gradually because the denominator here, 1 minus beta t, will become 1. So it has a vt as itself. By using these exponentially weighted averages, we can optimize our standard gradient descent with momentum. So this is a standard gradient descent method we used before. And as you can see in the vertical axis, it has a huge oscillation. So we have slower learning rate here, slower learning on our model in this image. So we want to have slower learning on the vertical axis, but faster learning on the horizontal axis to reach the global minimum faster. So the momentum algorithm follows that we update, we get v dw based on the dw we get from backpropagation, and also v dv based on the db. And to update parameters, we don't use the dw and db we used before, but instead of doing that, we use a v dw and v db to update our parameters. Because this vdb and vdb is is derived from the averages, weighted averages. So if we assuming that the vertical axis is corresponding to the W parameter, and vertical axis is corresponding to the for the W is a horizontal axis, and for B is a vertical axis. We may get by averaging it a uh, relatively large VDW because it has all the same direction. But as you can see, about the dB sometimes go up and it sometimes go down. So these averages, uh, average of these directions will be relatively smaller than dW, so that we can get the result that we want. Next one is RMSprop. It's quite similar to the momentum wave, but we use another notation, SDW and SDB, which is we use a square of derivatives. So intuition for that, um, let's take a d slope. So if we assume that the vertical axis is W and the horizontal axis is B, then delta W is relatively smaller than delta B. So the delta B square, um, which is dB square, will be relatively large and it makes SDB large. And on the other hand, dW is relatively smaller than dB, and it will make the SDB relatively smaller than the SDB. And when we update, we use this SDW and SDB. So we update W faster because we divide the dW with a smaller number, but we learn about the B slower because we divide the dB with a larger number. And as you can see, the RMSprop, we can improve learning paths like green color paths. So that's all for today's recording, and thanks for watching.